we have one main tutorial that we will focus on today, which is this one here on using FHI-aims for embedded cluster simulations in ChemShell. Excuse the wrong image here down below. But the main person responsible for the tutorial and delivering the material is Oscar van Vuren. So he's here also from Cardiff University. And I will hand over in a bit for him to go through the tutorial material. This link will also be posted in the chat in a bit. And and then you should all be ready to have essentially a terminal window open where you're on the cluster, as well as the online material in a browser window. That will be the setup that Oscar is also using. Now, before we go to this tutorial, I wanted to briefly hand over to Gabriel. So Gabriel was also a speaker yesterday in our webinar. And he was also kind enough to give you a quick intro to the Embassy specific tutorial. So Embassy is this QM wrapper we now have also that works with FHI-aims. And Gabriel has prepared a tutorial. As far as I know, it's still somehow in development stages. So please, remember that if you have any questions or more sophisticated use cases, you are free also to contact Gabriel after the webinar, or even during if you have specific questions to Embassy. But I would then quickly hand over to Gabriel to just do a very few minute introduction to his tutorial as well.
Very much for the introduction, Konstantin. Yes, so if you came to the talk yesterday, that's great. But if you didn't, just as a small introduction, Embassy is a Pythonic wrapper that is designed to perform QM and QM embedding. So whether it's DFT and DFT embedding or wave function and DFT embedding, it essentially just allows you to describe one small bit of your system with a high level of theory and the rest of your system with a lower, less expensive level of theory. That's the absolute cliff note, the two-sentence summary. And if I can just share my screen for a second, I'll just show you the tutorials. So the reason we're probably not sharing this more widely is because we're going to go to 1.0 release soon. So some of this may be subject to change, but I think the broad strokes of this tutorial should still apply. There'll just be a few extra features that might need explaining, or some alternative ways of working which are better than what is presented here. So everything here should still apply, but perhaps it'll be updated with some more sophisticated best practices. So it's structured in the same way as quite a lot of other FHI-aims tutorials. It'll just give you the initial splash page, and then what's it doing? Okay, there we go. So this tutorial, it'll go through the installation instructions. The installation instructions for Embassy are relatively simple. You just pip install Embassy. There might be some dependencies that we need to resolve while we're updating all of the dependent packages, but this will be the end state where you just pip install Embassy and then it'll just work on your machine. And then for FHI-aims, all of the dependent infrastructure and machinery is already merged into the main branch of FHI-aims. And you just compile it, you're following the standard instruction set. But the only thing that you would need to include is this build shared libs instruction set. So you need to compile FHI-aims as a shared object library that the ASI interface then loads in and then just calls the FHI-aims runners and initialization processes. And running the Embassy calculation once you've installed this is hopefully relatively simple. So the tutorial that we have here goes over an example test case that you saw, that you might have seen in the webinar yesterday. So this is where you load in the library, just point it in, point to the species path, and it uses a lot of the syntax for the ASE library. So these are the main steps down here to run Embassy. You load in the projection embedding object, you load in the atoms objects that you define through the ASE interface, and then you define the embedding mask, with one being the high level of theory, two being the low level of theory, and then you define your two calculators in the standard ASE syntax, but you would ordinarily apply the low level of theory to calc low level, and then calculator at the high level of theory with either like a hybrid level of theory or a total energy correction method such as RPA. And then there's lots of other defaults that you can fiddle around with, which change which projection functions that you use, whether you're running the wrapper in parallel But most of these things just work under the hood. So realistically, once you set up the projection of the object, it's relatively simple and ready to go. And then the second part of the tutorial goes over the other section we were talking about. So we spent a lot of time talking about truncation and basis truncation. And it goes over some of the things that apply for the RPA tutorials, such as the selection of your basis. So whether you use the numerical atomic orbital based valence correlation consistent basis sets and how you extrapolate those, and also ways of applying the basis truncation with the given threshold. So for the version 1.0 release, most of this should still stand. We'll have an alternative form of performing the basis truncation. So this is where you just truncate the entire basis set, and also support for spin polarized systems, and at some point K-point functionality as well. So the vast majority of what's in this tutorial will stand. It's just before we go to the 1.0 release, we just want to make sure that all the I's are dotted and all the T's are crossed. So if you want to go ahead and use it anyway, feel free to go with the understanding that it's subject to change, but I will probably make an announcement on the Slack when everything is solid and in place. Thank you very much.
Great, thank you, Gabriel. I just posted the link to the QMQM embedding tutorial also in the chat, so it's already publicly available, so feel free to take a look. As Gabriel mentioned, it's subject to change, but you're also free to write in our general FHI-aims Slack channel, so that's our community channel, in case of any questions, and we can forward questions to Gabriel, of course, as well, or you contact him directly. Great. Then we would go ahead with the larger part of today's tutorial, so that will be the embedding tutorial with ChemShell and FHI-aims. And for this, I would hand over to Oscar, who will try and walk you through the tutorial. In case you have questions, as always, use the Q&A function here in this webinar setting, or raise your hand if you ask a question and so on. So we are free to answer questions also during the actual tutorial. But this I would hand over to Oscar, and then Oscar, please go ahead. Thank you.
Great, thank you very much, Konstantin. So let me just quickly get my content up. It's over here. So yes, today we're going to be going over the interface to ChemShell with FHI-aims. So this allows us to do explicit multiscale embedding using the FHI-aims framework. So I'm Oscar. Yeah, I've been working with this interface for about 4 years. So I've got a lot of experience, but I don't necessarily claim to be the most knowledgeable person on embedding, but hopefully we can go through this together and we can all learn something. So to begin with, we're going to do a very quick recap of theory, because if you haven't been in the webinar, you might not understand the impetus or what we're doing. So what we're doing here is we're doing what's called QM-MM embedding. So we have a QM density functional theory calculation, which is what we're using FHI-aims for, and we're going to embed that into a classical environment, so something modeled with a force field representation of interatomic forces. So this allows us to access potentially more expensive density functionals than we might otherwise be capable to do with our system, and it also gives us some of the benefits of using a cluster representation over a periodic representation that Andy very kindly elaborated on yesterday. So to do this, we basically take our FHI-aims cluster calculation, our aperiodic calculation, and we place it into a set of shells of point charges. And these point charges are fitted to represent the long-range electrostatics of our material. So in this case, we're looking at magnesium oxide, so we need to make sure that our Madelung potential is well represented, for example. We construct our total energy in this additive scheme, where we basically take the sum of our QM and MM, and then the interface between QM and MM. Anyone who's paying attention will remember that there was a polarization term yesterday in Andy's equation, the same equation, which will come up later. So this is all implemented in ChemShell and does all the energy summations for us, and it's very nice in that way. So we can just effectively run these calculations relatively easily. So the tutorial comes in 3 parts. Part 1 is software setup. We're not doing part 1 because Constantine has very kindly worked with the MS1P team to set up a functioning ChemShell binary. This is potentially a very challenging step depending on your HPC architecture. So take your time, and compiling ChemShell is not easy, but you can get there. The instructions in part 1 are relatively comprehensive, I think, though that's yet to be seen on various other compiler stacks, and we'll see how that goes. So what we're going to do today is we're going to start from tutorial part 2, which is embedded cluster preparation. Now, I just said that software setup is the most challenging step. If you get the software working, then building your cluster and constructing your embedded cluster such that it is an accurate and effective representation of your periodic material is a very difficult and potentially time-consuming step in this process. Ultimately, if you don't build your cluster right in the beginning, then your results that come out of it will never be as accurate as you want them to be. So it's really worth spending quite a lot of time and thought and effort building these clusters and understanding how we do this and how we do this effectively. So to achieve that, we are going to, hopefully I can use that. Get rid of that. And then we should be here. So hopefully you can see now my terminal and the tutorial on the other side. So yeah, basically I've just been through very briefly what's going on in terms of the QMMM method and ChemShell. So for the tutorial we're doing today, there should be a directory in your home space called reference files that contains all the reference outputs for this for these calculations and construction methods, and we will need to copy in some the calculation files. So we're going to go straight to step 2. So we need the script cluster preparation.py that is in the part 1 section. So if we go into part 1, we can type properly, and we look at cluster preparation. So this script, as it's presented in the tutorial, is an entire work through for how to turn a periodic model into an embedded cluster model. There are a few steps here that we might want to think about, but for the most part, this is relatively holistic. And we see that here you go. We need to take the shared tutorial files part 2 contents of this directory, and then we can use them to run our clusters. So we start from a periodic model. And I think the easiest way, at least for me, to generate a periodic model in the Pythonic environment that ChemShell is built in is probably using ASE. ASE has a bunch of very helpful functions and allows us to build periodic models relatively easily. So what we've got here in the first few lines is we're constructing a periodic model of magnesium oxide. So we're using here the bulk functionality in ASE, but actually, ideally, we'd like this to be a relaxed geometry rather than just a geometry we've constructed without doing any kind of geometry optimization. But for now, we're just building a structure, a rock salt MgO structure. We've got the lattice parameter 4.212. This is an experimental lattice parameter. This is why we might want to do a relaxation. And then we're also forcing it to be cubic. This just helps a little bit with the construction methodology, but is not strictly necessary. We do not need to have an orthogonal unit cell, but it does help a little bit. And then we're writing this out so we have some posterity for our file. Then we're beginning our looking to ChemShell, and we're importing all of the ChemShell procedures, and we're specifically importing this input-output tool that allows us to very easily take an atoms object, so an ASE atoms object, and turn this into the equivalent in ChemShell, which is called a fragment. So a fragment is specifically designed for this kind of QMMM embedding and holding the slightly different data structures that might be required for a QMMM model over a regular density functional theory or just a general periodic model using one type of theory. So that's why I want to use this fragment object. And that's what we're doing here. We're taking our periodic model, we're converting it to a fragment, and we're just telling ChemShell that the bonding in this material is ionic. This just helps ChemShell construct a connectivity matrix, which is an important part of this fragment property. So the next step is that we need to add charges. So because we're using a classical model, we need to make sure that our classically represented regions have the point charges that we want them to have. So we add our formal charges to our magnesium and cations and oxygen anions, and then we add these shells. These shells model the polarizability of the oxygen, so they allow for they allow for polarizability, and part of the polarizable force field embedding scheme, and these are well documented as part of force field methods. So what we do is we add a fitted charge over the top, and the sum of the oxygen core and shell, you can think of it as potentially something like a core and valence electrons, should sum to the formal charge. So the core of this will have a positive charge of 0.79, and the shell has this negative charge. So overall, the ion remains O2 minus formally, but it allows for the polarization. So then once that's done, we've set up our geometry properly. We then take our fragment and we use construct cluster. So this method basically cuts our periodic model into a cluster by effectively just expanding the periodic images and then just selecting everything in a spherical region from a given origin. So we're choosing to select from an atomic position, so in this case atom 0, with a radius of 30, and then we're doing some coordination scale adjusting of charge. This adjusts the charges on the outside of the cluster, determining active radius and how we're fitting the external point charges for the long range potential. So once we've done that, we then have this cluster object. This is still here. And then once we have this cluster, we then need to split it up, right? We can take our cluster, but it's not very useful if it's just all one region. So we need to split it up into the different regions we want. So the first thing we do is we need to define which atoms in this cluster are going to be QM and which are not going to be QM, right? So we do this by defining a QM region. In this case, we're taking the range from 0 to 33. So this is just a very simple QM region selection method. There are more sophisticated methodologies that one can and probably should use. But in this case, we're just selecting the first 33 atoms. So this creates a shell, right? So we take our atom 0, which is an oxygen, and then we're taking the first shell of magnesiums around that, so that makes a 7, and then we're adding another shell on top of that. So we end up with a roughly spherical QM region. So once that's done, we then actually have to tell ChemShell that we want to split our cluster into these different regions. So we use this cluster.partition method. This tells ChemShell how do we want to split up our cluster into the different regions. So we say the QM region is what we just told it. It's these first 33 atoms. Cutoff boundary tells ChemShell how much space you want for your boundary pseudopotentials, which Andy discussed yesterday. So this is the interface region. Then we have the active region. So this is how big the sum of the active QM and active MM regions are. So this is the parts of the cluster that are allowed to relax. The nuclear coordinates are not held constant. where the origin of the cluster is, so that we know where to place the QM region within that cluster, and the explicit interface. And we're also saying that in our interface region, we don't want to have oxygen anions, because we don't have an oxygen pseudopotential. So we've excluded all of our oxygen anions from our interface. Once this is done, we have this partitioned cluster, and we write it out to the ChemShell punch file format. So this punch file format is the sort of recommended I/O format for ChemShell. It lets us write out, for example, again, in the same way a fragment is built for embedded cluster models, this punch file is also built for embedded cluster models. It contains the geometry, it contains all the shell information, charge information, connectivity information. So it's probably the best way to do file I/O within the embedded cluster structure. And we also write out as an XYZ just so we can visualize it and make sure that we've built a cluster that is sensible. So if we run this, we should be able to probably call Python on this, though I imagine if we go to shared ChemShell bin. So what I'm doing here is making sure that we're actually running the ChemShell binary on this file, because it's a Python file, so we could just call Python 3 on it, but if we do that, then we need to make sure that ChemShell is in our Python path, which we could check, but this is just simpler. So this is the cluster cutting workflow. It gives us some nice information, and we should see that if we run this, we see partitioned cluster saved, ChemShell exiting normally, and we should see that we've got now these partitioned clusters, partition cluster.pun. So this is the file containing all of the coordinates, shells, charges, all the information we need to do our embedded cluster, and then our partition cluster.xyz, which should just look like cluster.xyz should look like you're expecting it to look like. So we have a number of atoms and then just XYZ coordinates for all of the cluster. Great. So I'm going to give everyone a couple of seconds to make sure that they've all run that. Just have a quick look, see if there's any questions in the Slack channels.
Yeah, just as a side note, the Python path is correctly set up on the cluster, so you're also free to simply run Python _cluster preparation. Yes, and that should basically do the same. As Oscar said, you can also directly call the binary, but the result will be the same.
Yep, the result is exactly the same. So we can just call Python 3 on this, but we can also run our shared cluster. So yeah, these are just the commands that you need to run this. So we're going to wait for another few seconds to make sure that everyone has followed on, because we will need these files to do the next step, because they form the geometries that we'll be running our calculations on. So if we want to be able to run our single point energy evaluations, we need these files. So just make sure that everyone is up to speed. Perhaps I can have a quick look at the punch file format. So you see that we have, it's a lot like an XYZ file. We have our coordinates, but we also have these we see that things are labeled MG1 or O1. So this is the region labels. So region 1 is our QM region, region 2 is our interface, region 3 is active MM, region 4 is frozen MM, and region 5 is point charges. So this, whilst the XYZ didn't contain this region information, the punch file does, and we see here we've got some O3s, MG2s, and then hopefully if we go down far enough, we'll see some O4s. And then we'll finally see, if we go right down to the bottom, that the point charges are just given the label F. This is just convention based on the way that this software was originally written. In principle, it can be any label, but the developers have chosen to stick with F. If, of course, you want to model something that contains fluorine, you might want to change this. But for most materials, this isn't a problem. So,
I think there's a question from the audience. Let me allow Omar to speak. Omar, I think you're able to speak now.
Sorry, I have a permission denied MGO bulk XYZ, so I couldn't run the script.
So you copied over the tutorial files and then, so you basically did the comment here on the right hand side of Oscar's browser window. And then you ran just a Python script and got this error.
Yeah, I was running the Python script and then I got this error, permission denied, MGO bulk.xyz.
That's problem. I'm not sure. Let me check.
I mean, I don't think we're using this file, so you can just comment that line out and just try running it again. That'll be the simplest outcome.
Yes. Otherwise, we can check also your user directory in a second.
Yeah.
Then we'll just let you know if we find the issue.
Yeah, Omar, just to check that you're running the Python script from your home directory. So, yeah, not from the shared directory, because then if you try and run things in the shared directory, then you may get a permission error. But if you run in your home directory, then it should work. If not, then something else is going wrong and we'll try and figure it out.
Okay. So yes, my mistake. Thank you.
Yeah, exactly. So if that's the issue, then we would recommend just running the comment you see basically in the purple box, which first copies all the shared files to your local folder. Because you have to do the work in your user folder, otherwise you will get these permission errors, if that was the reason.
So hopefully everyone has now had time to run these this cluster construction. If you haven't, please continue to run it. It's we need this geometry file for the next step. So hopefully I'm going to just leave here, and if you please put a comment in if you want to see those commands again. But we're going to go on to running a calculation and how to actually perform the calculation. We've just set up our cluster, but how do we actually perform calculations? So the first thing we need to see is if we go into 3A single point, we just want to run single point calculations. Again, we've got to import our import functions from ChemShell and then construct our geometry. What I want to actually highlight here is this is how we're defining the QM theory, QM calculator to be used by ChemShell in this calculation. So we've got two files here. We've got a settings file and a basis file. Now this is, I think I mentioned, it's not the only way to build the calculator. Actually, ChemShell usually goes through a kind of defining an exchange correlation function or defining a basis set. But I thought that actually sticking with these two files will be the most familiar to users of FHI-aims, and also sort of keep things a little consistent. So these two files should, when combined, become the control.in, right? So basically, this is the control.in split into two parts, into the physical model that we're using that contains, the model, and then the SCF convergence parameters output keywords and all the keywords that are available in control.in. And then the FHI-aims.basis contains the basis sets that are then concatenated into the end of that. So if we have a look, we can look at FHI-aims.settings. So you see here we're defining our exchange correlation function, or spins, relativistic. So we need to specify a few things. First off, this QMMM keyword, this allows for the calculation of forces on point charge centers, and this allows for the electrostatic embedding in FHI-aims. This is well documented in the manual, so if you want to really read the nitty-gritty of how this of what this does, then do go and read the embedded cluster section of the FHI-aims manual. The second thing we need is this override initial charge check. So this is an override for behavior that FHI-aims, if the sum of the charges in geometry.in is not the same as the overall charge control.in, FHI-aims will stop, because it asks for you to do a reasonable guess of your initial charge distribution. So we're overriding that behavior here because we're using a cluster model where we haven't explicitly defined the charges on our region one, on our QM region. This is not ideal, but it's fine. But ideally, you can define your initial charges, and I've provided in this script somewhere a little Python snippet that helps you do that. So let's put this here so that everyone in the webinar knows how to get all the files. That's probably a good place to start. So yes, that's what the override initial charge check does. This is important for these models because we haven't set up our charges in our geometry, but you probably should if you're going to do these calculations. We're also defining various things like occupation mixers, charge mixing parameters, and then our SCF accuracy parameters. So that's the first part. And then if we just have a quick look at the basis set file, you'll see that we're using our pseudopotentials. So this is how we're defining our our pseudowise species. So we have the species PQMG2E. So this is our magnesium 2, as in magnesium in region 2, not a magnesium 2 ion. So it is a magnesium 2 ion. And then we're defining where the pseudopotential is defined. So we have this .cpi file, which is, I think, generated using FHI-PP98, but there are other pseudopotential generators available that are more accessible and a bit more available. So we have our pseudopotential. The next thing in here should be, yes, our empty sites. So we're just defining our what our empty sites are. We need these to make sure that we're not doing that we're removing grid points on the integration grid close to the point charge centers, the monopole centers. This helps with stability and removes Coulomb singularities. So we need these. They don't have any basis functions on them. We remove if we go up here, we remove the minimum basis, and then we comment out all the other basis sets. So they're just they're for controlling the grid construction. And then we have our normal species descriptions that you might be familiar with, that we have to make sure they are labeled correctly. So, for example, this is the oxygen default, but it's labeled oxygen 1, for example. And the same goes for magnesium. So, we're going to now look at our back to our single point calculation. So I've just gone over that. Up here we have a couple important things that we need to define. So we can get our total charge for our QM region. This is important for when we're setting up our calculation, and actually what the QM region is. That's very important. And then this frozen region is the regions that have their nuclear coordinates constrained. This is not strictly necessary for a single point calculation, but we'll put it in here because it's just best practice to define it. It doesn't hurt. So yes, we just defined our settings and our basis. We're saying what the species for the ghost atoms are, what the minimum cutoff is to make sure that they are in the right place, and then what the charge on our total cluster is. So we've just defined that from our total charge. Then we quickly define our MM theory. So we have this force field file. This is fitted to the PBE data, so that when we have our PBE calculation and our PBE force field calculation, hopefully we should end up at the same geometry. So this is to try and eliminate strain in the QM region, across the QM-MM boundary, sorry. So this is using GULP, General Utility License Programs, is a quite common materials modeling force field package. So with those two levels of theory defined, we then combine them in this QMMM object. So we have our QMMM theory, the fragment, so the geometry that we're going to run this theory on, what the QM region of that fragment is, what the coupling is. So this basically controls how we're doing the interface region. So here we're saying ionic, or to the pseudopotential type interface, and the number of self-persistent shell optimizations. So this allows for the polarization of the MM region based on changes in the QM region. And then finally, we define the calculation we're going to do. We're going to do single point, and then we run it. And then if we were going to do an optimization, we would then save the outputs of the geometries here. So that's this file here. And then I'll hopefully walk through the script, and you can read this in your own time. Here we go, talking about the charge. So this is how you set your initial charges. If we were going to, we're not going to, but this is a sort of Python snippet on how to do it and how to include it in the calculation. So we're now going to submit our calculation to the cluster. We see we just got a normal Slurm control. So if we just sbatch, hopefully now this should run this calculation for the single point if we run this in the single point job. So if we just wait a few moments to make sure that people are following along and are running these calculations.
Yeah, you're also free to ask any questions now, since we have a few minutes of waiting time anyway.
Yes, of
Maybe
course.
there are some questions from the audience.
And just as a reminder, so if you didn't set up the cluster in part 2, then you can go back and do that before submitting this single point calculation. And in the tutorial, in all the kind of purple boxes with the test tube is kind of the cheat sheet or commands you enter on the command line in the terminal here to kind of follow all these steps. So creating the directory, copying the reference files over, and then submitting calculations.
Yes, and when you're on the cluster and waiting, you can also always check the queue. So in case you're maybe not super familiar with Slurm, if you just type SQ in your terminal while you've submitted, you will see basically all the running jobs. So you see, for example, here the job from Oscar is still running. And this gives you an overview of how long your calculations has been running. I believe for this first part, this is roughly 3 minutes or so, or 4 minutes.
Yeah, it's not a very long calculation. The single point is fine, but we are doing the self-consistent shell optimization. So what this means is that whilst this is a single point calculation, we are actually running multiple FHI-aims calculations. So it does take a little bit longer than you might expect for this kind of but that's just the nature of the embedding. You have to make sure that it's self-consistent, of course. So once mine has finished, we will just see what's at the end of this. Let's just run FHI-aims. Just wait for this to finish before I move on.
While we are waiting, I have actually a question for Oscar.
Okay. Yep.
So you showed a lot of different parameters to different Python objects. Are they documented somewhere? So can people just read the documentation?
Yes, though the ChemShell documentation is a little bit, I think, a little bit lacking. But if we, I think, at the end of here, yes, so the ChemShell manual here contains a lot of information in terms of how do we do cluster construction and materials such as this. So this contains a nice overview of the cluster construction, and actually contains construct cluster and how everything works. I think actually the best source, the best documentation for ChemShell really is the source code. So this does contain a bit more of the theory, for example, what each region's doing. And I'm also going to lightly plug my work doing automated cluster construction workflows. So this methodology, which we're not using here, but which in future I may update the FHI-aims tutorial to use, basically somewhat automates this process and allows you to use effectively some predefined defaults that are sensible for these cluster construction, and it also has some warnings and making sure that everything works. So that's somewhere else you can go. But yeah, the user manual is quite. It can be a little obtuse, but it's quite good usually.
And yeah, just for anybody wanting to find this manual, so if you just Google ChemShell, go on the website and click on documentation, then there's actually 2 different versions of ChemShell, or say 2 different interfaces, shall we say. So there's PyChemShell, so the Pythonic version of ChemShell, which is what Oscar was showing and also what we're using. And there's also the TCL ChemShell, which I believe is an older interface for ChemShell, or an older way to use ChemShell, shall we say. But yeah, on the documentation, both of these versions are there, and I'll just send in the chat the documentation for the PyChemShell that Oscar was showing.
Yes, so originally ChemShell was written in TCL. It was then rewritten in Python. TCL ChemShell is no longer supported, but does still work. So it's strongly recommended that anyone starts with Python, because TCL is going to fall behind. In fact, if you just want at the bottom of part 3, there's the ChemShell tutorials themselves, which goes through a little bit more of what ChemShell can do and best ways to do things, and then also the manual. Both of these link directly to the Python ChemShell versions. So let's just check. There we go. Okay, so my calculation is finished. So let's just have a quick look at the output file. 3a.log. I could type, that would help. There we go. So this contains some of the information about the process and just some of the logs of what we're doing, and then it goes through. Okay, we've run our FHI-aims library, we've run our gulp interface. Again, so like we say, we're doing our self-consistent shells, so we have to rerun them again. We see that our shells a few more times, and then finally, we should get to the end, and we should get a QM energy, conversion QM energy, conversion MM energy, total energy, and then our final single point energy. So once that's done, then this nice chemshell XT and parallel computer. So that just helps us keep on top of the running the chemshell and how it all works. So if I just check the queue very quickly again and see. So I think very quickly we can just move on, given that we've got it's 10:02. So yeah, just very briefly, of course, we can choose our QM region size if we want to have a calculation that runs locally on a laptop, for example. You just take the steps to 7, reduce the number of shells by 1, and that just, of course, makes our calculation a lot more tractable, and then we can do that on 8 CPUs rather than 64 we're using here. So we're not going to do the relaxation because it takes about half an hour. But ultimately, we want to be able to do relaxations. Chemshell can do relaxations, and that's something that you might want to consider doing. Again, if you can access all of these files as part of this tutorial, and potentially you can go through the relaxation as well to see what the outputs of that look like. It's very standard, but it's maybe worth looking if you're interested. So we're going to skip the optimization, and then we're going to go to a little bit of an applied outcome. So what we want to do here is calculate an ionization potential. So this very simply is the energy difference between the cluster at its normal charge, at its ground state charge, and then we just ionize it. We just take an electron out, add a positive charge in, and then the difference between these two is the ionization potential. There's also, again, a polarization term that is included as a Yost correction. That's covered in the chemshell the actual chemshell tutorial on the chemshell website on how to do that properly and calculate accurate ionization potentials. But here, because we're going to be using our single point unoptimized geometry, this means that we and our ionization potential will be not inaccurate, but not very precise. So the main difference here is we're taking the exact same geometry, partition cluster.pun, doing most of the same things. The only thing we're doing slightly different is we're adding 1 to the QM charge. So we're just saying take the charge on the cluster and then just add 1 to that. So that just again adds our positive charge, removes our electron, and then because we're doing an ionization, so we are expecting to pull an electron out of it. That's the sort of process we're modeling, pulling the electron out of, for example, off of an oxygen anion. We're then just initializing the spin for that ionized atom. And then everything else is the same. So if we're initializing a spin, that means that our control.in will need to change. So we have this FHI-aims _ ionization .settings. And this is exactly the same, except we've just changed the spin from none to colon here to make sure that FHI-aims is calculating our spin properly. So there's nothing else really to mention. These two are almost identical to the previous calculations, except for those 3 lines. So again, we can submit this calculation, and this calculation takes a little bit longer. Though actually, I remember now there was another important element. Yes, so this calculation will time out if we just submit it. So it's important that we modify one of the parameters so that this runs on the cluster in time for the tutorial, and that's the shell max cycle. So that's the number of self-consistent shell relaxations we're doing. Now, because we're doing a collinear spin calculation, the SCF cycle in FHI-aims takes significantly longer for this calculation than it does for the ground state single point. So to basically eliminate that, we're just going to change this to be, let me just go to insert mode. Yeah, change this to be 1. That just means that we're only going to do one self-consistent shell cycle. That means our shells will not be relaxed self-consistently, but it does mean that our calculation will run in time for the tutorial to finish. So then we say...
Yeah, just as a side note, we slightly adjusted the wall time for the calculation for this part. So it is possible to run. Just note it takes a bit more than 10 minutes. If you reduce the shells here, max cycles to just 1, it will of course run faster. So we leave that up to you. Yeah, it still works. So it should still work
works in
fine.
20 minutes. Okay.
Exactly.
Wonderful. So this is not strictly necessary.
No, fact, it's not strictly necessary, but makes it quicker.
If it's not
maybe
necessary, then I will undo my changes, because this is it's not it was just that was a demonstration case to make sure that these calculations ran. If we don't do this self-consistent relaxation, then our final and the total energies will of course be incorrect. So now we can just dispatch our submission, and then we should see now that our calculation is right. Wonderful. So this will give us a final energy. Again, important to note that chemshell and everything, all the chemshell outputs and inputs need to be in atomic units. So just be aware. Some core people out in the past that I've worked with, that they are getting particularly converting between angstrom and Bohr for distances. So just be aware of that. That's why everything's coming out in Hartree. We do our calculations in Hartree. So once this finished, you should see that you get a final total energy, and then we can construct using our equation that we should get about 5.9 electron volts for this ionization potential, which is sort of closely in agreement with literature for GGA level calculation, though of course quite far off the experimental at 7.6. So I'll put this back here for submitting the calculation, and I think we'll just wait to see the output of the calculations and see if there's any questions from anyone.
Exactly. It's a good time for questions, since we usually wait now 10 minutes or so for everything to run. So of course, feel free to just submit, and then we have time for any questions you might have. There can of course be more advanced questions, also anything beyond the tutorial. So if you are, this is now a good point to open up the discussion rounds. As a reminder, we have Gabriel here as well, so you can of course also ask questions for the QM part. So feel free to take this time to ask questions. If there's anything you need help with on the cluster, you're also free to simply ask questions about that. And as always, you are free to use the text-based option, so just type in the Q&A section. Or the alternative, you can simply raise your hand and we can allow you to speak if you would rather verbally describe your question to us. So that's both fine. So please feel free to ask anything.
I wonder if perhaps in this intermediate time we can have a little look at the other tutorials that are available on the ChemShell website, just to have a brief sort of overview of what else you can do. So this is not just this sort of material, this sort of modeling scheme is not just applicable to magnesium oxide, of course, and do other ionic materials. But if we have a quick look at the ChemShell tutorials and the case studies, particularly, you'll see modeling an MgO surface. So of course, we're doing bulk here, but all of this same methodology applies to surfaces. So we can do surface modeling, we can do reactivity on surfaces. But for example, particularly, we might want to look at doing zeolites. So we might want to look at aluminosilicates, and then we're doing it's much the same in terms of running clusters, but there's a few other considerations to take into account when we're doing covalent materials. For example, the embedding scheme, this sort of interface scheme, is a little bit different because we're cleaving through covalent bonds rather than, ionic materials. So if we have a quick look, see, we need to cut across one of these bonds, and this is done by adding a link atom. So if we're doing covalent systems, we also then need to add a proton link atom to our calculation basis set. But that's for slightly out of my area of expertise. I don't really run this kind of calculation model, this kind of material. But again, I'd be happy to direct people if they want to do this kind of modeling on where to look for the right information to make that work. Ooh, go back here. So yeah, this calculation will take its time. So feel free to ask questions, or go and get a coffee or something. Now's a good time to do it.
Yeah. Also, one more note: if you look at the queue right now, you'll see that the status of some jobs is CF. That means configuring. So, well, that means that some additional nodes for the cluster are fired up for the demand. So this firing up nodes takes about 3 minutes. So don't be afraid. So if you see this status, that means that your job will be run in 3 minutes.
Maybe since we have some time here, we quickly mention the part 3b, which we haven't gone over in detail, but maybe you can mention a few words there as well. So I think that was the relaxation workflow. So
Yeah,
this
of course.
calculation
So
takes too long, but we are able to simply look at the reference files. Yeah.
yes, so if we look quickly at the reference files for 3b. So yeah, we're not running this calculation, but we see that we have a few differences. So if we look at the optimization, again, everything should seem very similar to the single point, but instead of running a single point, we run this optimization opt. Give it the same theory, max cycle. So this is the number of geometry optimization steps we're doing, the algorithm we're using. And this is where we need to add the frozen. So this makes sure that our regions 4 and 5 that are not supposed to relax, the nuclear coordinates are held fixed, are in fact held fixed and don't relax in a way that we don't want to. And then we're also making sure that we're outputting the entire path. And of course, we run the optimization, and then once this is completed, we save the optimized geometry so that the file is relatively sensible. What we get is we get this DL find directory. So this is the so this contains all of the geometry optimization steps. So DL find is the geometry optimization library containing Camshell, and this contains, for example, the geometry of step 0 through 10 as punch format, just the active region as punch and XYZ, QM region as punch and XYZ, then all of our aims output files for these different calculations, all of our gulp input and output files, as well as more aims input, control.in, geometry.in. So you see that this is going to take 10 times as long as our single point, because we're doing 10 geometry steps. So it's very much the same, but we also get this full path, and then we see we can plot the profile with Chemshell comes with a plotting functionality using matplotlib. So we can plot using this profile opt, and that shows us our energy over a number of steps. It also comes with some restart checkpoints and various other files that are important for the restart. So that's kind of the optimization. It's very similar to the single point, but yeah, I think the important things to mention is that we're using DL find, so it's a geometry optimization library that's part of Camshell, and that this contains all of your geometry optimization steps. And if we very quickly look at the output file 3b.log, you'll see that there we go. So there's a big banner for DL find. You're going into it, and it's got a different citation. So that's important, and then it also tells you what it's optimizing and how that's running. It contains various it contains all of your outputs and things that you might be looking for in your things. So you get QMM total energy for this step has been calculated. Then it writes the output for that step, tests our convergence. So we're looking at convergence cycle 3. It's testing our convergence against our parameters. So it outputs all of this, tells us whether things are converged, and then looks to run again. And of course, it's a regular BFGS optimization cycle. So this lets us, using DL find, lets us actually access the kind of relaxed geometries that would normally be used to see out of FHI-aims in periodic boundary conditions or in cluster cases, and this lets us do things like very simply you could absorb molecules on surfaces and lets you optimize those geometries and find other ground states. So that's ultimately, if you're using this software, that's where you'll want to be looking, doing relaxations. But again, we can't do them for this part of the tutorial. Plug my laptop in. Okay, wonderful. My calculation has finished. So if we now look in our 3c.log, just look at the end of it, we get the nice chem shell executed normally. It's nice. This is the same as your, very much the same as your have a nice day. So make sure that you just check to make sure that's in there. And then this, of course, contains our total energy that went out of it. So we see here we get our single point energy, which should match. Or am I looking in the wrong file? Maybe I'm looking in the wrong file.
No, I think you're looking at the single point on the right. You have to scroll down a bit.
Oh, I'm looking in the wrong. Oh, thank you, Constantine. All over the place. There we go. That looks about right. So then we see that we get this number out, and then we do our calculation to take our ground state energy from our ionization energy. We get the energy of our ionization potential overall. So that's, I think, the end of what I have to present. We'll wait a little while longer for people to run their calculations and to ask any questions if they have any.
Yes. Thank you so much, Oscar, for guiding through the tutorial itself. Now, of course, this is a specific example on the ionization potential of magnesium oxide, so you can do, of course, more sophisticated stuff. Oscar has already pointed out the online documentation for ChemShell and all the examples they have. So, and of course, you've seen yesterday also in a talk from Andy all the possible types of systems one can simulate with this scheme. So you're also free, of course, to think of more sophisticated examples. But hopefully the ChemShell installation works for the people who are interested, as well as the connection to FHI-aims. So this should all be possible. For the ChemShell specific stuff, we usually refer to the ChemShell site. So if you have any questions there, go to the webpage and look at the documentation or ask the responsible people. They probably are able to help you in that regard. Of course, if you need some help in the FHI-aims side. So there's one comment we maybe need to make in the FHI-aims part. For this specific integration with ChemShell and PyChemShell, we're using FHI-aims as a library, as a shared library. So that requires a specific comment in the FHI-aims build script, which is also mentioned in part 1 of this tutorial. So we have skipped over this a bit because on the cluster we have prepared everything for you in advance, so you don't have to mess about with the installation itself. But hopefully the explanations in part 1 are enough for you to get a working installation, if this workflow is interesting for your work.
Yes, and of course, if people are interested in using this workflow and with FHI-aims, then of course contact me on the community Slack or by email. My email's on the top of the tutorial. Very happy to help out and to get people using embedded cluster modeling. Yeah. And again, happy to help out with installation and things as well.
Great. Are there any questions? I think we are still waiting on one calculation or so on the cluster, but maybe we have some questions now. Can also just be a discussion round. So of course, if you're just interested in if this is applicable to your own work, feel free also to ask questions in this direction. Okay, I see one question from Raji. I will allow you to talk. So you should be able to unmute and ask a question.
Hi, can you hear me?
Yes.
So thanks for the presentation. Just a quick one. Can you please share with us the reference for the theoretical foundation of this approach, so that we can have a firm grasp of the basics, you know.
Of course. So I think there are two literature references here that we should have a quick look at. Let me just again very quickly open up my screens and share it. Okay, so we should be looking. Let me see if I can bring them up on my Zotero. That might be the simplest solution. So the first one is this paper from Sherwood. This is, I can share the DOI. It's called Quasi, a general purpose implementation of QMMM approaches applications of problems of catalysis. So this is the foundational paper for Chemshell, for the original TCL version of Chemshell. And this goes through basically what they're trying to do with Chemshell, how it works, and the outcomes that they want from it, and some applications. So this is really the foundational paper for this kind of for this Chemshell method, and it contains quite a nice overview of embedded cluster modeling for the applications that they're looking at. So that's the sort of for the very foundational papers for August 2003, and then for the version we're using, then there's this paper from Yulu, which is about the Python redevelopment of Chemshell. So this basically reiterates on the work that was presented in previous paper, but goes over much more the Pythonic implementation and the development, of course, that's happened in Chemshell since it was since the Quasi paper was published in 2003. So of course this is 20 years on. So this elaborates over some of the other materials and problems that Chemshell has been used to solve, and how it's all been redeveloped. So if I can, that's sort of the overview of, that's probably the two papers I'd recommend you read. If I, yes, thank you, Constantine, he's beating me to it. And there's the DOIs are in the chat, so that you can have a read of those, and that really will give you a very good overview of embedded cluster modeling using Chemshell.
Yeah, there's maybe one more, which I think is also linked in the tutorial section. So that's a recent review by Gabriel, who's also here.
Yes.
Specifically for heterogeneous catalysis. So if that's something you're specifically interested in, feel free also to have a look at that review. So it's more about QMMM simulations in the field of heterogeneous catalysis. So that might be more specific. But
yes, and of course, going through the references in Gabriel's review will, of course, give you all of the things that you need to find. So I think, yeah, those two papers would be the foundational QMMM papers, and then Gabriel's review is very good for applications in heterogeneous catalysis. And of course, if you can simulate that, simulate any heterogeneous system and that sort of thing. So yes, that's my is my recommended reading for this method. So checking the cluster, it seems that all calculations are finished. Again, happy to wait around and ask any questions, but Constantine, I think we're coming to the end of the time.
Yeah, exactly. We have roughly 10 minutes. So as a side note, we just want to mention the cluster will be shut down after the session and will reopen later on for the second session. So maybe you're still interested in running something again or whatever. You are still able to do this in the second session, but we recommend to copy over all the files that you might want to have on your local machine. So if you have run these kinds of calculations now and want to have the reference files specific from what you just ran during the tutorial, you are free to copy these over to your local machine. So for this, you can use the rsync command. If you check the README in your home folder, you should also see the comment again copied in there. So there are some more details also in the README, which is in your home directory. So in roughly 10 minutes, we will close the cluster, just so you know, as a heads up. If you want to save any of your work, please do so beforehand. And yeah, otherwise we still are open for questions or more remarks. But hopefully, Raji, this was already helpful in terms of literature. If you have other questions, just raise your hand again if you like.